You see it in every space movie. The crew of the starship walks around the bridge, sits in chairs, and sips coffee just like they would on Earth. When a red alert sounds, they run down hallways. Gravity is just there, it's a given. But then you watch real footage from the International Space Station. Astronauts are floating. Their hair stands on end. They push off a wall to get from one place to another. A drop tool doesn't fall, it just hangs there in the air. So, what's the deal? Why is gravity in space so different in fiction and in fact? And the bigger question, can we create the movie version? Can we make artificial gravity? The short answer is yes, we can. The long answer is that it's incredibly difficult, expensive, and it wouldn't work the way it does in Star Trek. It's one of the biggest engineering hurdles we face if we ever want to become a truly spacefaring species, traveling to Mars and beyond. It's not a luxury, it's a necessity to understand why. We first need to understand why living without gravity is so bad for us. Our bodies are built for Earth gravity. Every part of you, from your bones to your heart to the fluid in your inner ear, is designed to work against a constant downward pull. Take that pull away, and things start to go wrong. It's a bit like a car designed to drive on a road suddenly being put in the water. It wasn't made for that environment, and the consequences show up quickly. The most famous problem is with our bones and muscles. On Earth, every step you take, every time you stand up, you're putting stress on your skeleton and using your muscles. This constant work tells your body to keep those systems strong. In zero gravity, you don't walk, you float. So your legs, which are used to carrying your entire body weight, suddenly have nothing to do. Your body is ruthlessly efficient. If a system isn't being used, the body stops wasting resources on it. So, it starts to break down bone and muscle tissue. Astronauts can lose 1 to 2% of their bone mass for every month they spend in space. This is like having a case of aggressive osteoporosis. Their muscles atrophy or waste away. To fight this, astronauts on the ISS have to exercise for about 2 hours every single day. Use special treadmills with harnesses that hold them down, stationary bikes, and a resistance machine that lets them do things like squats and deadlifts. It helps, but it doesn't completely stop the decay. It's a constant battle just to maintain a fraction of their earthbound strength. Then there's the fluid problem. Your body is mostly water. On Earth, gravity pulls all that fluid down. Your heart has to work hard to pump blood up to your brain against that pull. In space without gravity, the fluid in your body redistributes itself. It shifts upwards into your chest and head. This is why astronauts often have puffy faces and skinny bird legs in their first few days in orbit. It also means their heart doesn't have to work as hard to get blood to the brain. Like any other muscle, if the heart doesn't have to work hard, it gets weaker. This fluid shift also causes other issues. The increased pressure in the head can lead to persistent headaches. More seriously, it can affect their vision. Many astronauts experience something called spaceflight-associated neuroocular syndrome, or SANS. The pressure can actually change the shape of their eyeballs and swell their optic nerves, leading to farsightedness and other vision problems. For some, their vision returns to normal after they come back to Earth. For others, the changes are permanent. And it doesn't stop there. Your vestibular system, the tiny organs in your inner ear that give you your sense of balance and orientation, gets completely confused. It's used to feeling the pull of gravity to know which way is down. Without that signal, it goes haywire. This leads to space sickness, which is a lot like motion sickness, with nausea, disorientation, and vomiting. Most astronauts get over it after a few days as their brains learn to rely more on their eyes for orientation. But the confusion is a constant background noise, so living in zero-G is tough. It's manageable for a 6-month stay on the ISS, but what about a trip to Mars? That's a 6 to 9 month journey just to get there. Then you'd spend time on Mars and then make the long trip back. We're talking about years in a low-gravity or zero-gravity environment. The physical toll would be immense. By the time a crew arrived on Mars, they could be too weak to perform their jobs, with brittle bones and weakened hearts. If we are ever going to explore the solar system in person, we need to solve the gravity problem. We need to bring a piece of Earth with us. We need artificial gravity, okay? So, how do we do it? The most straightforward and physically sound way has nothing to do with magic gravity plates on the floor. It has to do with spinning. Think about a common experience. Imagine you're on a merry-go-round at a playground. As it starts to spin faster, you feel a force pushing you outwards. You have to hold on tight to stay on. Or think about swinging a bucket of water around in a circle over your head. If you swing it fast enough, the water stays in the bucket even when it's upside down. It's being pushed against the bottom of the bucket. That outward pushing feeling is what we can use to simulate gravity. The scientific name for this is centrifugal force. It's not a true force like gravity is. It's actually a consequence of inertia. Inertia is the tendency of an object to keep moving in a straight line. When you're in a spinning spaceship, your body wants to travel in a straight line. But the floor of the spaceship keeps getting in the way, constantly pushing you towards the center. That constant push from the floor on your feet feels exactly like the push of the ground on Earth. Your body can't tell the difference. The floor becomes down. So the simplest way to create artificial gravity is to build a spacecraft that rotates. What would that look like? The most common design you see in science fiction and in real NASA concepts is a giant wheel or a torus, which is just a donut shape. The classic example is the space station in the movie 2001: A Space Odyssey. It's a huge, slowly rotating wheel. People live on the inside of the outer rim, where the spin creates a force that feels like gravity. Another design is like a dumbbell. You could have two modules, maybe a habitat and a counterweight, connected by a long cable or a rigid boom. The whole thing would spin around a central point, like two kids holding hands and spinning in a circle. People in the habitat module would feel a pull towards the floor. This design might be easier to build and launch than a massive solid ring. This sounds simple enough in principle, just spin the ship. But the details are where it gets incredibly complicated. Two factors determine how much gravity you feel, how fast the structure is spinning, and how big it is its radius. To create the feeling of 1g, Earth's gravity, you have a trade-off. You can either have a small structure that spins very fast, or a very large structure that spins very slowly. And this is where we run into a major problem: the human body. While our bodies can be tricked into feeling the push of the floor as gravity, our inner ears are not so easily fooled. The same vestibular system that gets confused in 0G also has a big problem with rotation. If you're in a small, fast-spinning centrifuge and you turn your head, you will feel it. It's called the Coriolis effect. It's a weird, disorienting sensation. If you move your arm toward the center of rotation, it will feel strangely light. If you move it away, it will feel heavy. If you drop a ball, it won't fall in a straight line, it will curve. Looking from side to side can induce powerful vertigo and nausea. It would be like living on a permanent tilt-a-whirl. No one could live or work effectively in that environment. Experiments have shown that humans can get used to a certain amount of rotation, but not much. Most researchers agree that a rotation speed of more than 2 revolutions per minute RPM is probably too much for most people to handle comfortably long term. 1 RPM would be even better. So, if we have to keep the spin slow, at 1 or 2 RPM, how do we get 1g of artificial gravity? The only way is to make the radius enormous. The math shows that to get 1g at a comfortable 1 RPM, you need a wheel with a diameter of about 1.8 kilometers, or over a mile wide. That's a colossal structure. The International Space Station, which is the largest thing we've ever built in space, is about the size of a football field. We're talking about something 10 or 20 times bigger. The engineering challenges of building such a thing are staggering. You can't launch a mile-wide space station in one piece. You'd have to launch dozens, maybe hundreds of modules and assemble them in orbit with robots and astronauts. The materials would have to be strong but lightweight. The cost would be astronomical, likely in the trillions of dollars. How do you power it? How do you maintain it? How does another ship even dock with a massive spinning object? These are not small problems. Because of these challenges, some have proposed that we don't need to simulate a full 1G. Maybe less is enough. We know that 0G is bad. We know that 1G is good. But we have no data on what happens in between. What about the gravity on Mars, which is about 38% of Earth's, or the moon's gravity at 16%? Would living in Martian gravity be enough to prevent the bone loss and muscle atrophy? We just don't know. It's possible that a smaller, more achievable rotating habitat that produces, say, 1/3 of a G would be enough to keep astronauts healthy on a trip to Mars. It would make the engineering much more manageable. A ship producing Martian gravity at 2 RPM would only need a radius of about 85 meters, which is much more feasible than a kilometer-wide behemoth. But we need to do the research to find out. A small-scale rotating module attached to a future space station could be a critical experiment, housing astronauts for months to study the long-term effects of partial artificial gravity. So rotation is the only way we know how to create artificial gravity that is even remotely within our grasp. It's an engineering challenge, not a physics one. But what about the stuff from the movies? The gravity plating on the USS Enterprise, where you just flip a switch and gravity turns on. Is that possible? To answer that, you have to understand what gravity actually is. For a long time, we thought of it as a force, an invisible rope pulling objects together, as described by Isaac Newton. But then Albert Einstein came along with his theory of general relativity and gave us a completely different picture. Einstein said that gravity is not a force, it is the curvature of space-time. Imagine a stretched out rubber sheet. That's space-time. Now, place a bowling ball in the middle of it. The bowling ball will create a dip, a curve in the sheet. That's what massive objects like planets and stars do to space-time. Now, if you roll a small marble past the bowling ball, it won't travel in a straight line. It will follow the curve in the rubber sheet and circle around the bowling ball. That's what we perceive as gravity. The Earth is just following the curve in space-time created by the sun. We are stuck to the Earth because we are in the deep gravity, well, the curve in space-time that the Earth creates. So to create gravity like Earth's, you would need to recreate the mass of the Earth. You have to squeeze the mass of a planet into the floor plates of your spaceship. That is obviously impossible. So, is there any other way to bend spacetime? This is where we leave engineering and enter the realm of highly speculative theoretical physics. Scientists have ideas, but none of them are close to reality. One idea involves a hypothetical particle called the graviton. In theory, gravitons are the particles that carry the force of gravity, much like photons carry the electromagnetic force. If we could somehow generate and control gravitons, maybe we could create a gravitational field. The problem is, we've never detected a graviton. We're not even sure they exist. And if they do, they would be incredibly difficult to interact with. Another far-out idea is negative mass. In theory, an object with negative mass would repel normal matter. It would bend spacetime in the opposite way, creating a hill instead of a well. You could potentially use a chunk of negative mass below the floor and a chunk of positive mass above the ceiling to create a gravitational pull downwards. But again, we've never seen negative mass. We have no idea if it can exist or how to create it. It's purely a mathematical concept for now. So the Star Trek style press a button for gravity is not on the table. It would require a fundamental revolution in our understanding of physics, a discovery on the level of Einstein's relativity. It's fun for fiction, but it's not something we can build. There is, however, one other way to create artificial gravity that is perfectly sound in terms of physics. It's called linear acceleration. Einstein's equivalence principle states that the effects of gravity are indistinguishable from the effects of acceleration. If you are in an elevator in deep space that is accelerating upwards at 9.8 meters per second, squared the same as Earth's gravity, it would feel exactly the same as standing still on Earth. The floor would be constantly pushing up on you, creating a perfect 1G environment. This is the kind of artificial gravity depicted in the show and book series The Expanse. The ships are built like skyscrapers. The engines are at the bottom, and the crew decks are stacked on top of each other. When the engines fire, the ship accelerates, and the force of that acceleration creates the gravity. The floor is down, towards the engines. To travel from Earth to Mars, they would burn, or accelerate for the first half of the trip, creating 1G for the crew. At the halfway point, the ship would flip around 180 degrees and then decelerate for the second half of the trip. This deceleration would also feel just like gravity, allowing the crew to live in comfort for the entire journey. This is a brilliant solution. It provides gravity, and it also gets you where you're going much, much faster than just coasting. So why don't we do this? The answer, in one word, is fuel. The amount of fuel required to constantly accelerate a spaceship at 1G is mind-bogglingly huge. Our current rockets, which use chemical propellants, are nowhere near efficient enough. They are designed for a short, powerful burst to get out of Earth's atmosphere. They can't sustain that thrust for days or weeks. The tyranny of the rocket equation, which relates a ship's change in velocity to its mass and the efficiency of its engine, is brutal. To achieve that kind of constant acceleration, almost the entire ship would have to be fuel, leaving no room for people or cargo. For constant thrust gravity to become a reality, we would need a propulsion revolution. We need something like a fusion drive, an engine that harnesses the power of nuclear fusion, the same process that powers the sun. A fusion rocket would be thousands of times more efficient than a chemical rocket and could potentially produce the kind of sustained thrust needed. But functional fusion reactors on Earth are still decades away, let alone miniaturized, reliable versions that can be put on a spaceship. So, like gravity plating, this method is also in the realm of future science, though it is perhaps more plausible. So where does that leave us? We're back to spinning. It's the only game in town for the foreseeable future. It's clunky, it's big, it's expensive, but it works with the physics we know and the technology we can imagine building. We haven't tried it on a large scale yet. There were some very early experiments in the 1960s during the Gemini program where a capsule was connected to an empty rocket stage by a long tether, and they were set to rotate. The experiments had mixed results and were difficult to control, but they did show that the basic principle worked. The ISS was originally designed with a centrifugal accommodations module, which would have been a place to do experiments on animals, materials, and artificial gravity. It was canceled due to budget cuts. Today, the ISS has some very small centrifuges for experiments on things like plants and mice, but nothing for humans. In a way, the ISS's primary mission is to study the effects of zero-G, so adding a large artificial gravity section would defeat that purpose. The next steps will likely be smaller and more cautious. Future commercial space stations, or the planned lunar gateway station that will orbit the moon, might include a small rotating module. It could be a place for astronauts to spend a few hours a day to get a dose of gravity, almost like an exercise machine, to help offset the effects of zero-G. This would also be a critical research platform to finally answer the question of how much gravity is enough. Building a full-fledged interplanetary ship with a large rotating habitat for the crew, a real-life version of the ships we see in movies like The Martian or Interstellar, is the long-term goal. It represents a massive commitment of resources and a significant leap in our space construction capabilities. It would be a project on the scale of the Apollo program or the ISS itself. Creating artificial gravity isn't about luxury or making space travel more like a movie. It's about a fundamental biological need. Humans evolved in a gravity field. We are creatures of the planet. To leave the planet for good, or even for a few years on a trip to Mars, we need to take that environment with us. We can't change our biology, so we must change our ships. The path forward is clear, even if it's difficult. It won't be with magic anti-gravity generators or super efficient fusion drives, at least not for a very long time. It will be with brute force, it will be with giant spinning structures carefully engineered and assembled piece by piece in the void. It will be a testament to our willingness to solve immense problems in the pursuit of exploration. When we finally build one, it will be one of the most significant steps we have ever taken on our journey to the stars. We will finally be able to walk, not just float our way across the solar system.